Welcome! In this session, we'll dive into LeetCode problem number 1232, check if it is a straight line. Our goal is to explore whether all given points in a 2D plane form a single straight line. We'll analyze the problem, consider different approaches, and break down the concept step by step. Let's get started. In this problem, we are tasked with determining whether a set of points lies on a straight line in a 2D plane. The input is given as a 2D array called coordinates, where each element represents a pair of integers, the x and y coordinates of a point. For instance, if we have a point 2, 3, it means the x coordinate is 2, and the y coordinate is 3. Our goal is to analyze all the given points and decide if they align perfectly on a single straight line. If they do, we return true, otherwise, we return false. This will involve checking the consistency of the relationship between the coordinates of the points, which we'll explore further in the examples. To clarify, let's look at some examples. In the first example, the input is 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. The output is true because all these points lie on a straight line. The slope, which is calculated as the change in y divided by the change in x between any two points, remains constant. For instance, between points 1, 2, and 2, 3, the slope is 3-2, / 2 to 1 equals 1, and this holds for all other points as well. In the second example, the input 1, 1, 2, 2, 3, 4, 4, 5, 5, 6, 7, 7 produces false because the points do not form a straight line. While some pairs, such as 1, 1, and 2, 2, have a slope of 1, the slope between 2, 2, and 3, 4 is 4-2, / 3 to 2 equals 2, which is different. Lastly, in the third example, 0, 0, 0, 1, 0, -1, 0, -2, the output is true because all points lie on the vertical line defined by x equals 0, confirming that they align on a straight line. Now, let's talk about the constraints and edge cases. The number of points in the array ranges from 2 to 10,000, so we need to ensure our solution can handle large inputs efficiently. Each point contains exactly two integers, and the x and y coordinates can range from -10,000 to 10,000. Additionally, there are no duplicate points in the input. Some edge cases to consider include the minimum input size of 2 points, which always forms a straight line since any 2 points define a unique line. We also need to handle vertical lines, where all x coordinates are the same, and horizontal lines, where all y coordinates are the same. It's important to use integer arithmetic for slope calculations to avoid precision issues with floating point numbers. Finally, the solution must remain efficient and scalable even for the maximum input size of 10,000 points. To determine if the given points lie on a single straight line, we can consider 3 different approaches. The first is the brute force approach, which relies on calculating the slope between every pair of points. The intuition here is simple: 4 points to lie on a straight line, the slope between any 2 of them must be constant. To implement this, we calculate the slope using the formula y2 y1 / x2 x1 for all pairs of points and verify that they match. However, this method has significant drawbacks. First, the time complexity is n², because we need nested loops to compute slopes for all pairs, which becomes inefficient for large inputs. Second, division introduces potential pitfalls, such as encountering division by 0 when the x coordinates of 2 points are the same. These limitations make this approach suboptimal for this problem. A more efficient solution is the optimized approach, which uses the concept of vector cross products to check for collinearity. This method avoids direct slope calculations and instead relies on the property that 3 points are collinear if the area of the triangle they form is 0. Mathematically, this can be verified using the cross-product formula x2 x1 * y3 y1 = y2 y1 * x3 x1. To apply this, we fix the first point as a reference and iterate through the remaining points, comparing the cross-product for each subsequent point. If any cross-product is non-zero, the points are not collinear. This method is highly efficient, with a time complexity of n, as we only need to compute the cross-product once per point. Additionally, it avoids division, which eliminates precision issues and edge cases like division by 0. This makes the cross-product approach both robust and computationally optimal. Another possible solution is to sort the points by their x coordinates and then calculate slopes sequentially. The intuition is that, once sorted, the slope between each pair of adjacent points should be the same if the points lie on a straight line. To implement this, we first sort the coordinates array based on x values, then compute the slope for every pair of consecutive points, ensuring that the slope remains constant throughout. While this method is straightforward, it introduces unnecessary overhead due to the sorting step, which has a time complexity of n log n. Although this approach works, it is less efficient compared to the cross-product method, as sorting is more time-consuming than the linear time traversal used in the optimized approach. After evaluating the options, the optimized approach using the cross-product is the most efficient and reliable solution. This strategy stands out due to several key observations. First, it avoids division, which eliminates potential issues with precision and edge cases like division by zero. Second, the linear time complexity of n makes it particularly suitable for large inputs, ensuring the solution remains scalable. Additionally, the mathematical insight that collinearity corresponds to a zero cross-product simplifies the implementation. Compared to the brute force method, this approach reduces time complexity from n squared to n by avoiding unnecessary calculations for all point pairs. While the sorting-based method is valid, its n log n complexity is less efficient than the linear time complexity of the cross-product approach. Overall, this optimized strategy is fast, simple, and robust, making it the best choice for solving the problem. The final complexity of the chosen strategy highlights its efficiency. With a time complexity of n and a space complexity of 1, this approach is well suited for solving the problem in an optimal manner. The linear time complexity ensures that the solution scales efficiently with the size of the input, while the constant space complexity reflects its minimal memory usage. Together, these characteristics make the cross-product method the most effective and reliable choice for determining if the given points lie on a straight line. To determine if all the points in a 2D plane lie on the same straight line, we rely on the concept of slopes. A straight line is defined by a constant slope between any 2 points on the line. For this problem, instead of directly calculating the slope using division, which can lead to floating point precision issues, we use cross products to perform the comparison. The formula for the slope between 2 points is the difference in their y-coordinates divided by the difference in their x-coordinates. However, by rearranging this into a cross-product comparison, we avoid division altogether. Specifically, for 3 points, the cross-product ensures that the relative slopes are consistent without introducing rounding errors. This forms the mathematical foundation of the algorithm, allowing us to verify collinearity efficiently and accurately. The algorithm begins by calculating the slope between the first 2 points, which serves as the reference for the rest of the points. Using the cross-product method, we can then iterate through the remaining points and compare their slopes relative to the first point. If any point deviates from the initial slope, we conclude that the points are not collinear and return false. The algorithm handles edge cases as well. For example, if there are fewer than 3 points, the points are trivially collinear, since a straight line can always pass through 2 points. For the base slope calculation, we compute the differences in x-coordinates and y-coordinates between the first 2 points. These differences, dx and dy, are then used to evaluate the slopes of all subsequent points. When iterating over the remaining points, we calculate the cross-product for each point relative to the first point. This involves checking if the difference in y-coordinates multiplied by dx equals the difference in x-coordinates multiplied by dysprosium. If this equality fails for any point, the points do not lie on the same straight line, and the function returns false immediately. If the loop completes without finding any deviation, we can confidently return true, indicating that all points are collinear. Using the cross-product comparison not only avoids floating point precision issues but also ensures that edge cases, such as vertical lines where dx equals 0, are handled seamlessly. This method is both robust and efficient. The problem involves an input array of 2D points, where each point is represented as a pair of integers. The output is a Boolean value indicating whether all points lie on the same straight line. To support the calculation, we use additional variables like dx and dy to store the differences in x and y for the base slope. These variables are reused for each cross-product computation, making the algorithm space-efficient. In terms of complexity, the algorithm runs in n time, where n is the number of points, as we iterate through the points once. The space complexity is 1, as the algorithm does not require any extra data structures. This efficiency makes it suitable for handling large datasets. Finally, any edge cases, such as fewer than 3 points or vertical lines, are naturally accommodated within the algorithm structure. The Python implementation begins by checking the base condition. If there are fewer than 3 points, it immediately returns true. For the main computation, the differences in x and y for the first 2 points are calculated as dx and dysprosium. These values are then used to iterate over the remaining points in the input array. For each point, the algorithm uses the cross-product formula to determine if the slopes are consistent. If any point violates the collinearity condition, the function returns false. If no violations are found, the function returns true at the end. This implementation is clean, efficient, and leverages the mathematical insights to ensure accuracy while maintaining optimal performance. This implementation solves the problem check if it is a straight line by leveraging the mathematical property of slopes between points on a straight line. Here's the step-by-step explanation. 1. Extract the first 2 points. The first 2 points in the coordinates array are used to calculate a reference slope. These points are denoted as x0, y0, and x1, y1. 2. Calculate slope differences. The differences in the x-coordinates, dx equals x1, x0, and y-coordinates, dy equals y1, y0, form the numerator and denominator of the slope, respectively. These differences are used to check collinearity for all other points. 3. Iterate through remaining points. For each subsequent point, x, y, in the coordinates array, we verify whether the point lies on the same line. This is done using the cross-product formula, y0, asterisk dx equals x x0, asterisk dysprosium. This formula avoids division, preventing potential issues with floating point precision. 4. Return result. If any point fails the collinearity check, the function immediately returns false. If all points pass, the function returns true. This approach ensures that the solution is efficient with a time complexity of n, where n is the number of points. It also handles edge cases such as vertical and horizontal lines, as the cross-product formula applies universally without requiring special handling for undefined slopes. This is the Java implementation for LeetCode problem number 1232. Check if it is a straight line. The logic mirrors the provided Python solution. The key differences include explicit type declarations, the use of Java's array indexing for coordinates, and the structured method definition within a class. The implementation verifies if all points form a straight line by calculating the reference slope using the first 2 points and checking the consistency of this slope using a cross-product approach for all subsequent points. To determine if the given points lie on a straight line, we start by extracting the first 2 points. Here, the coordinates are 1, 2, and 2, 3. These 2 points will serve as our reference to calculate the slope of the line. The slope is based on the differences in their x and y values. So, we compute dx, which is the difference in x-coordinates, as 2, 1, giving us 1. Similarly, dy, the difference in y-coordinates, is 3, 2, which is also 1. This gives us the reference slope, which we will now use to check the alignment of the remaining points. Now, we proceed to validate the slope consistency for the other points in the input. For the point 3, 4, we calculate y0, asterisk dx and x0, asterisk dy. Substituting values, we get 4 to 2, asterisk 1 equals 2 and 3 to 1, asterisk 1 equals 2, which means the slopes match. Similarly, for the point 4, 5, the calculations are 5 to 2, asterisk 1 equals 3 and 4 to 1, asterisk 1 equals 3, confirming that the slope remains consistent. Finally, for the point 5, 6, we find 6 to 2, asterisk 1 equals 4 and 5 to 1, asterisk 1 equals 4, again confirming consistency. Since all points maintain the same slope as the reference, the output is true, indicating that the points lie on a straight line. In another example, we check if the given points form a straight line. The input coordinates are 1, 1, 2, 2, 3, 4, and 4, 5. First, we calculate the slope using the initial 2 points, 1, 1, and 2, 2. Here, dx equals 2, 1 equals 1 and dy equals 2, 1 equals 1. This gives us the reference slope. Next, for the point 3, 4, we compute y0 asterisk dx as 4 to 1 asterisk 1 equals 3 and x0 asterisk dy is 3 to 1 asterisk 1 equals 2. The results are not equal, indicating that the slope is inconsistent. Because one of the points breaks the pattern, the output is false, confirming that these points do not lie on the same straight line. Finally, let's consider an example where the input points form a vertical line. The coordinates given are 2, 3, 2, 5, and 2, 8. Starting with the first 2 points, 2, 3, and 2, 5, we calculate the differences as dx equals 2, 2 equals 0 and dy equals 5, 3 equals 2. Here, the 0 value for dx indicates a vertical alignment. Next, for the point 2, 8, we calculate y0 asterisk dx as 8 to 3 asterisk 0 equals 0 and x0 asterisk dy is 2 to 2 asterisk 2 equals 0. Both expressions evaluate to 0, confirming that the slope is consistent. Since all points align vertically, the output is true, verifying that the points lie on the same vertical line. The time complexity of this solution is O(n), where n represents the number of points in the coordinates list. To break this down, we start with the reference slope calculation. Extracting the first 2 points from the list and computing the differences in their x and y coordinates are constant time operations, so these steps take O(1). The primary work happens during the iteration through the remaining points. Here, the algorithm loops from the third point to the last one, which results in n2 iterations. For each iteration, it performs a constant time operation to compute the cross product and check if the points align. This loop, therefore, contributes O(n) to the overall complexity. When we combine the O(1) from the initial setup and the O(n) from the loop, the total time complexity simplifies to O(n). The space complexity of this solution is O(1), meaning the algorithm uses constant space regardless of the input size. This is because it does not require any additional data structures that grow with the number of points. The input list of coordinates is provided externally and does not count toward the algorithm's space usage. Within the algorithm, we only use a fixed number of variables such as x0, y0, dx, dy, and a few others to store intermediate values. Since this set of variables remains constant, the memory usage does not increase with the size of the input. As a result, the space complexity remains constant at O(1). To compare, a brute force approach to this problem would involve calculating the slope between every pair of points in the list. With n points, there are n choose 2 combinations, which results in O(n squared) slope calculations. Each slope would then need to be compared to ensure consistency, making this approach very inefficient. In contrast, the current optimized solution avoids explicitly calculating slopes repeatedly. By using the cross-product method, it ensures collinearity for all points in just O(n) time. This is a significant improvement over the O(n squared) complexity of the naive approach. When analyzing different scenarios, the best case, average case, and worst case time complexities all remain O(n). Even in the best case scenario where all points are collinear, the algorithm still needs to check every point. In the worst case, if the points are not collinear, the algorithm might detect this early but still needs to iterate through all points in the general case, maintaining the O(n) complexity. To mathematically justify the big O notation, we observe that the dominant factor in the algorithm is the iteration through the coordinates list, which involves n steps. Each of these steps performs constant time operations, such as calculating the cross product and checking for equality. The reference slope calculation and other initial operations are also constant time and do not depend on the input size. Since O(n) dominates O(1), the overall time complexity is O(n). Additionally, the space complexity is O(1), because the algorithm does not use any additional memory structures that grow with the input. It operates using a fixed number of variables, ensuring that the memory usage remains constant, regardless of the size of the input. When solving this problem, there are a few common mistakes to watch out for. First, incorrect slope calculations often arise when dividing by 0. For instance, if 2 points share the same x-coordinate, the slope becomes undefined. To handle this, it's essential to identify vertical lines separately and avoid direct division. Next, floating point precision errors can occur when comparing slopes using floating point arithmetic. Instead, rely on integer math, such as cross-multiplication, to sidestep precision issues entirely. Another frequent pitfall is neglecting edge cases, like when only 2 points are given, there are duplicate points, or the points form vertical and horizontal lines. These scenarios should be explicitly tested in your solution. Finally, it's easy to mix up the order of coordinates during slope calculation. Always stick to a consistent formula, subtract y coordinates first, then x coordinates, maintaining the order as y2 y1 / x2 x1. Hard-coding specific cases, like explicitly checking for horizontal or vertical lines, is another mistake to avoid. Instead, aim for a generalized solution that works for all types of input. From an interview perspective, this problem is designed to test your understanding of basic geometry concepts and your ability to systematically handle edge cases. Demonstrating efficient use of integer arithmetic can strengthen your solution by reducing precision issues and improving reliability. In terms of performance, the optimal approach should achieve O(n) time complexity, since each point only needs to be compared once. This is a great opportunity to showcase clean, efficient, and readable code. Additionally, you may encounter follow-up questions, such as checking whether points lie on other geometric shapes like circles, parabolas, or more complex curves. Be ready to adapt your solution for these variations. This problem is closely related to several others on LeetCode that involve geometry and pattern recognition. For example, LeetCode 1502, which asks you to verify whether a sequence forms an arithmetic progression, focuses on identifying numerical patterns. Another is LeetCode 1037, which requires you to determine whether 3 points form a valid triangle or lie on the same line. A more advanced problem, LeetCode 149, challenges you to find the maximum number of points that lie on the same line, adding complexity to your logic. Lastly, LeetCode 587, also known as Erect the Fence, dives deeper into computational geometry with the task of constructing a convex hull. Now, in terms of alternative approaches, one efficient method is to compute the slope between the first 2 points and compare it with the slope of all subsequent points. Using integer-based cross-multiplication here ensures that you avoid any precision issues from division. Another robust technique is the vector cross-product method. By calculating the cross-product of vectors formed by 3 consecutive points, you can easily verify collinearity without ever needing to calculate slopes explicitly. While there are efficient ways to solve this problem, it's worth mentioning the brute force approach as a contrast. This method involves calculating the slopes between every possible pair of points and comparing them to determine if they align. While conceptually straightforward, this approach is highly inefficient, with a time complexity of O(n squared, making it impractical for larger datasets. This emphasizes the importance of optimizing your solution and choosing the right strategy for the problem. Great work! To recap, we solved the problem by ensuring all points share a consistent slope, achieving optimal time and space efficiency. Remember to watch for edge cases and practice similar geometry problems for better understanding. Thanks for joining, and don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!